In this video, we'll see how to use hypothesis testing to test claims about proportions. What percentage of people do you think own smartphones? Jot down a quick guess off the top of your head. These kinds of things can be kind of fun to estimate. Okay, got your guess? So, according to Statista, 85% of US adults owned a smartphone in 2021. How does that compare to your guess? Was your guess lower or higher? Now, what if you were to think about just college students? Would you think that would be lower or higher than that 85% number? Personally, my hunch would be that it would be higher. So, let's say that you decide to test that claim and see if it applies to your college. That's another common use of hypothesis testing, taking a claim about an overall population and seeing whether the claim is true about a smaller subpopulation. We'll start by defining the parameter we want to investigate, the proportion of college students, at your college that is, who own smartphones. The null hypothesis is that the proportion for college students matches the proportion for the whole US, that there's no difference. And the alternative hypothesis represents your hunch, that the proportion of college students who own smartphones is greater than 85%. Let's also agree on a significance level for the test. 5% will do just fine. If our result from our data is so rare that it would occur less than 5% of the time, we'll reject the null hypothesis. Okay, time for data collection. Suppose you survey a simple random sample of 300 students. 273 of them say that yes, they do own a smartphone, while 27 of them say that no, they don't. Let's check our conditions. We already said that the sample was random, so that's good. Also, our yeses and nos are both at least 10, and 300 students is less than 10% of the population, assuming the college is large enough. So we should be good to proceed with our hypothesis test. We'll calculate p hat, which is our number of yeses divided by our total sample size, and that gives 0.91. That is, 91% of our sample said that they do own a smartphone. That is in fact above 85%. The question is it far enough above 85% to call that number into question? Let's put that p hat in context. If the null hypothesis is really true, that is, if 85% of college students own smartphones, then we can figure out the sampling distribution of the sample proportions. The mean would also be 85%, and if we plug that into our formula for standard error, square root of p times 1 minus p over n, then we end up getting about 2% for our standard deviation. Now we can use that mean and standard deviation to find out what's called the test statistic, which is the z-score for our p hat that we found. Take our p hat, 0.91, subtract the mean, 0.85, and then divide by the standard deviation, about 0.02, and we end up getting a z-score of about 2.91. Okay, so that's the test statistic. What do we do with it? Well, since our alternative hypothesis, our hunch, is that the proportion of college students owning smartphones is greater than 85%, that means we're going to use a right-tailed test. We're going to take our test statistic and figure out the probability that a given z-score could be greater than that z-score. Remember, we call that our p-value. So in our case, that's the probability that z is greater than about 2.91. We can calculate that with norm.s.dist. The s, remember, stands for standard, as in standard normal distribution. If we work that out, we get about 0.001805. That's our p-value, and so that's the chance that we get a sample proportion as large as we did, or larger. Now, our level of significance alpha was 0.05. Since our p-value is less than that rarity threshold, our conclusion is to reject the null hypothesis. Put in context, we would say that there is significant evidence that the proportion of college students who own smartphones is in fact greater than 85%. Note, by the way, that since your sampling frame only included students at your college, These results only generalize to students at your college. It doesn't call the original 85% into question. Rather, it shows that the 85% doesn't apply to this particular subpopulation. One last note about the type of test we used. We used a right-tailed test here in this problem because our hunch was that the true population parameter was greater than the original claim, and hence we needed to use 1 minus norm.s.dist. If, on the other hand, our hunch was that the true population parameter was less than the original claim, we'd use a left-tailed test. And we'd use just plain norm.s.dist. That's what it does by default, remember. And finally, if you're looking for a difference of any sort from your null hypothesis, but aren't sure which direction it'll be off in, you can use a two-tailed test, which takes both sides into account, finding the probability that you're off by a certain amount in either direction. You could calculate that by adding together the above two probabilities, but since we're doing everything in terms of z-scores, you can take advantage of the symmetry, using the negative absolute value to get the area for just the left half, and then multiplying by 2 to also give you the right half. It all depends on your alternative hypotheses. That's what tells you what kind of test to use and which formula will get you the result you'd need to make a conclusion.